Hi everybody, back to solid-state electronic devices by Ben G. Strudman. So problem, this one going to be your problem number 2, and we have actually 5 problems. Okay, that's what I studied at the University of Rochester back to 1995, and I rewrite the solution for everybody. For this one's still in chapter 2. It's about atomic and electrons. So the first problem is that read chapter 2.5, atomic structure and periodic table from the textbook, and answer the following questions. Actually, this one we look back of our atom structures before we move to electrical properties of materials. So it's a good time for us to recall, everything that we have learned before. A. What are the maximum numbers of electrons on the sp, d, f, and g subshells? B. What do the electronics configurations of our carbon, silicon, and germanium have in common? C. What are the electron configurations of ionized Na and Cl? That's from NaCl, right? For let's take a look at the atom structure. They ask you what is the maximum numbers of electrons on sp, d, f, and g subshells. So basically we have subshell, actually we have the atom shells look like this, starting from n equal to 1, n equal to 2, 3, and so on. And we know that we represent n as the principal quantum number, right? That's start from 1 to 3, and L, that's also a quantum number that start from 0 to n minus 1. And M, that magnetic quantum number start from negative L to L, and is simply a spin number. You have the plus and minus 1 over 2 h bar. Back to the atom structure that we have learned before. Now to see what is the maximum number of electrons on sp, d, f, and g. You take a look at the subshell S for the innermost orbital. That's for n equal to 1. So your L simply equal to 0, because the L equal to n start from 0 to n minus 1, right? And you still have S equal to plus and minus 1.5. So the number of electrons, the maximum number of electrons is going to be 2. That's for subshell S. Now for subshell P, you move to n equal to 2. This means your L going to be from actually 0 to 1, but if you consider only a subshell P, you have L equal to 1, then this is your magnetic quantum number going to start from negative 1 to L. So you have M become minus 1, 0, and 1, and this is your spin number. So you have a maximum electron to be 6, right? This one 2, 2, 2, 3 up 2, make 6. Subshell D, n equal to 3, L equal to 0 to n minus 1, or L equal to 2. And that's why you have a maximum electron to be 10. And you can work on a subshell F, n equal to 4, or L equal to 3. So maximum electron is going to be 14. Same as the subshell G, n equal to 5. The maximum electron going to be 18. I simply write the number of electrons on the SPDFG shell, going to be 2 n minus 1 plus 1, and then the whole multiplied by 2. Now, what about B? What do the electronics configuration of C, carbon, silicon, and germanium have in common? Okay, let's take a look closely. For this is for n equal to 1, 2, 3, 4, 5, and this is your L. And for n equal to 1, L equal to 0. This become 1 is, so you have total electrons 2. For n equal to 2, you have L equal to 0 and 1. That means you start from the innermost orbit. That's the become 2s. And you can take this one as the max as 2, right, for s. And p, the maximum electrons that can be confined in this orbit, going to be 6. So you have a total of 8 electrons. For n equal to 3, you have L equal to 0, 1, 2. So this turned out to be 3s, 3p, and 3d. And the maximum electron in the D subshells, that's what? 8, right? Okay, let's look back. Sorry, subshell D, that's maximum electron, that's going to be 10. So that's how you get 18. You have ASS2, PS8, that's make, sorry, PS6, 2, 6, and then D10, so that's 18. For n equal to 4, you have 4s, 4p, 4d, 4f. S make 2, P make 6, D make 10, that's 18. And F make 14, so that makes 32. And for G, you have what are the maximum number of electrons in the subshell G, that's 18. So you have G as 18, and plus 32, because you're ending at the subshell F, so that makes the 50, right? 18 plus 32, that's 50. So the electronic configurations for for carbon here, we have atomic number 6. That's going to be 1s, 2s, and 2p. That makes 6 of electrons, right? So this is the configuration of your carbon. For silicon, you have 14. For Ne, you can write this one. Ne is 10. That's atomic number. So you need 4 more. So that's going to fill up 3s2 and 3p2. Okay, for Ne, you can write the configuration as you want to make is 10, right? So Ne going to be for 1s2, 2s2, and 2p6. That's give you 10. Simply, this is the simple way to write the configurations of our silicon. And for germanium, you can see that why I put argon here on 18, because the at r n equal to 3, that's the you have a argon what that's the 3s2, 3p2, 3d10, right? So let's make 18. You start from there. So for sorry, what did I do? That's I put like 3. Oh, sorry, because there I forgot this one. For n equal to 2, 1 and 2, you have start from that. So you already have 10 and 18. Hold on a second, what did I do wrong here? You also have a 3d10. Sorry, for argon you have 1s, 2s, 2, 2p2, 3s2, 3p6, right? So let's make what? Our 18. Because p is 6, s is 2. So you have 18, so you need to continue with 3d10. And that make what? 28, right? You need 4 more. So you go to n are equal to 4. That's their 4s2 and 4p2. That's their the configuration of our germanium. So, and then what they have in common, if you noticed, is that they have 4 outermost electrons. So this is the outermost of for the carbon, you have outermost electron to be 2, right? Because this is the n equal to 2. And for silicon, outermost n equal to 3. So you still have outermost electron to be 4. And for germanium, same, because you have n equal to 4. And then the outermost electron is going to be 2 plus 2, that's 4. So they are the same outermost electron, which is 4. Now, what about our ionized Na and Cl? Ionized Na and Cl, which is their Na positive and Cl negative. Na for the normal Na, that's atomic number is 11. So you have Na positive. That means you lost 1 electron. So you have atomic number to be 10. Okay, or it's 10. So your 10 simply you pick up an E. That is there. 1s2, 2s2, and 2p6, right? This is the configuration. And for Cl negative, that means you have 1 extra electron. So you put like argon here, 18, same, right? Atomic number. And then you can go from 1s2, you need 18, right? This is 10, so you need another 8. So you end up only 3s2 and 3p6. This is their configuration for Cl negative. Problem number 2. Show that the electronic density of states in a one-dimensional system, or also called a quantum wire, is given by Rne. This is the density of states equal to 2m to the power 1.5 pi h bar to the power -1 and 1 over square root of E, where E is the energy, m is the electron mass, okay, or the mass. Let's see here what they are looking for. They want you to prove the density of states equal to these expressions. We'll take a look at the figure. This is the Fermi surface at energy EF. That's the Fermi level. And you have the components Kx, Ky, and Kz. In general, for 3 dimension, you have E equal to h bar square k square over 2m, or p square over 2m, right? Where k equal to the pi over L, where L is the cubic size. Let's assume that electron is confined in a box. In the K contained volume Kx, Ky, Kz. So that's become a 2 pi over L to the cube, because it's just like a cubic, right, or a box with the same dimension. And for the sphere, the volume of the sphere become 4 pi kf to the cube over 3. This is your kf, right? The radius of 4 pi r to the cube over 3. That's the volume of the sphere. Let's say E is the total number of states in the sphere. From the book, you may write E equal to 2 that's the volume of the sphere, and divided by the size of the volume of Fermi state, or actually you divide the volume of the sphere, Fermi sphere, by the volume of one state. That's give you the number of states, right? That's very simple. And why we have 2? Because one state we have the spin plus and minus 102. So that's why we put the factor 2 here. For one dimension, that simply become 2kf over pi L, because the k equal to pi over L. And then your E, that's a p square over 2m. So you have h bar square k f square over 2m, and you simply substitute kf. This is your kf pi over L, and then an E, because you get kf from this equation. Okay, something about the math. And finally, you have the total number of states in the sphere equal to this expression, and the density of states divided as in E equal to differential of the number of states with respect to the energy. You just do differentiate, and you have in E equal to this expression, same as as given in the problem. So you already verified how to get the density of state. That's the problem number 2. Now problem number 3. Assuming the concentration of electrons in AU n equal to 5.9 10 to 22nd per cubic centimeter. Use the free electron model to calculate the velocity of the fattest electrons, called also Fermi velocity, in AU. Compare the result. with the velocity of light, which is c equal to 3.0 10 to the 8 meter per second. Hint: the electrons occupy the end states of the lowest energy, namely those with the magnitude of k is less than magnitude over k max. Find k max first. Well, from the free electron model, this is the number of state from the textbook, and EDE equal to this expression, where V is the volume. So your N, simply you do integration with respect to the E, and do integration from the energies from 0 to EF. That's the Fermi level. Just plug in an E, and you can do integration. So what about this one? I simply write the two expression, just write EF in the term of N. Then your EF equal to this. So this one you have N over V. It's become the electron density by volume. So I simply put the N over V become N, and you can calculate for EF, which is in the term of what you have H. You have electron mass, that's the 9.1 10 to negative 31. N is given 5.9 10 to 22nd. Be careful, this one give you in per cubic centimeter. You need to convert to cubic meter. So let's make 10 to 28th. Okay, that's all you need. And I have EF equal to 8.88 10 to negative 19 joule. What next? Also, by relation EF and Kmax, EF maximum energy of electron, this also give up to Kmax. So your Kmax you can calculate because you already know EF, and you can calculate by this relation. I have for Kmax equal to 7.65 10 to negative 15th. But also, if you want to look for the velocity, right, of electron, you use this relation. Your EF simply equal to P squared over 2m. That's the momentum, and that's equal to kinetic energy. That's the 1.5 mv squared. So your V, that's the equal to this expression. You end up with V equal to 1.4 10 to the 6 meter per second. You can also be able to find the ratio of V and the C, which is the light velocity. So that's turned out to be about 0.5% over light velocity. Half and half. Okay, so that's what they ask you ask for. Calculate the velocity of the fastest electron. So that's the maximum energy rate of electrons that at the Fermi energy. Number 4, let me check my size. Okay, still have more space. Number 4, A. Calculate the lowest energy level expressed in electron volt for particle of mass 1 milligram. to be confined in an infinite one-dimensional quantum well of a size of 1 millimeter. So we move to the quantum well with the potential, or sometimes they call potential well. B, the mass of an electron in indium 0.53, gallium 0.47, arsenal is the 0.04 m0, where m0 is the mass of the free electron. If a one-dimensional quantum well is formed in this material with a size of 5 nanometer, ask you to calculate lowest energy of electron in eV, not in joule. So by looking at the potential well or quantum well with the size of 1 millimeter, and you have an infinite potential as the potential wall. From Schrödinger wave equation, in one dimension you have this expression, and this one actually comes from E equal to the kinetic energy plus the potential energy. Boundary condition, where you take a look at the solution of this of the Schrödinger wave equation first. From our basic math, your solution become psi of x, that's the wave function, right? That's equal to a exponential jkx plus b exponential negative jkx. And for this one actually become the forward moving from the left to the right, and this one is to become the backward moving of electrons. And your k is equal to square root 2 me over h bar. Okay, actually come from this term, the factor in front of the wave function. Now sorry, for sorry, you apply the boundary condition, you know that psi 0 equal to psi r 0, because you have no wave equation, beyond the potential wall. Right? This is your 0, this is your L. So just apply the boundary condition to the wave function. You end up with 0 equal to a plus b, or a equal to negative b. And also for psi L equal to 0, you have this term equal to 0, where e to the power jkl minus e to the negative jkl actually equal to 2j psi kl. That's equal to 0. That means this term have to be 0. So your kl need to be n pi, and your k are equal to n pi over l, right? Because the side are n pi equal to 0. And the energy En equal to h bar square k square over 2m. So you can apply your k, which is equal to n pi over l, in this equation. You have our term. M is the mass of a particle, which is the what? 1 milligram, right? You need to convert to a kilogram. So that's why I put the milligram is milli is 10 to negative third. So I add 10 to the 6th, and then 10 to the negative 6, 10 to the negative third, and 10 to the 6th. That's give you 10 to the 6th. 10 to the third. That's the kilogram. unit for kilogram. So you have left is the 10 to negative 6, and your L is the 1 millimeter, so that's the 10 to negative 3rd meter. So you have everything. So your En equal to 3.43 10 to negative 37th in square electron volt, because you need to divide it, this is in the unit of joule, you need to divide it by Q to have the unit electron volt. So the lowest energy is going to be at N equal to 1, or E1 equal to 3.43 10 to negative 37 electron volt. Now, what about B? Well, for B, you simply have a different mass, become a 0.04 m0, where m0 is the electron mass. That's the 9.1 10 to negative 31 kilogram. The rest still be the same, right? And actually the dimension is what? 5 nanometer. So that's make 5 10 to the negative 9th meter. You have En equal to this in the unit of joule. You divide it by 1.6 10 to negative 19th. That's give you in electron volt. So your lowest energy N equal to 1. That's E1 equal to 0.377 electron volt. That's the problem number 4. Now let's move to problem number 5, also about a potential barrier. But this one, let's see, we have a step potential. Electrons of energy E are approaching a potential step of the height V0 from this figure. So the Schrödinger equation for that problem to find A, the electron reflection coefficient R, for the case E less than V0, that's the electron energy, and V0, that's the potential. Also calculate the numerical value of R, that's the reflection coefficient, for energy equal to 0.5 V0. So this one E less than V0. B, the electron reflection coefficient R, for the case E greater than V0. And calculate the numerical value of R for E equal to 2 V0. In this case, E greater than V0. Is the behavior of electrons in this case the same or different than that of classical particles? Classical particles, the energy has to be greater than the potential to be electron to keep moving, or no reflection, right? See, for the case E less than V0, the distribution of probability, ask you to plot the distribution of probability. You don't need to calculate for any numbers of finding electrons inside the barrier. For example, x is greater than 0. Hint, for x less than 0, there are both incident and reflected electron waves, while for x that greater than 0, there is only the transmitted one. Okay, let's get started. You have electron coming in, and you have the potential V0, that's the potential step. For 1D problem, you apply Schrödinger equation, same. Now the region 1, this is your region 1, this is your region 2. Your V0 equal to 0. your v equal to 0, sorry, for x less than 0. And you have solution. I put this psi 1, that's the wave function in the region 1, equal to a exponential j k1 x plus b exponential of negative, you can either I or j, doesn't matter, k1x, where k1 equal to square root 2me over h bar. And the first term is the incident one, and the second term is going to be reflected wave function back and forth. Now for the region 2, now v equal to v0. So you have the wave function in the region 2. You have this term, right? Because your v0 not equal to 0. So the solution is that psi 2 equal to c exponential k2x plus d exponential negative k2x, where k2 equal to square root v0 minus e to m over h bar. Now this term is very important to be considered in the case of arbitrary E, or the electron energy. But let's consider the first solution first, the solution in the region number 2 for v equal to v0. Since you don't have this term, because what? Because for x become positive, for x greater than 0, you cannot have this term, because this term going to be increasing, right? That's not divided. So c need to drop. That means c equal to 0. You have only the exponential negative k2x for the wave function in the region number 2. Now in the region 1, you also apply the boundary condition. That means psi 1 have to be continue. So the wave function in the region 1 at 0 have to be equal to the wave function at the region 2 at 0. That's why you have a plus b equal to d. And also the different derivative of the wave function in the region 1 at x equal to 0 has to be equal to the derivative of the wave function in the region 2 at x equal to 0. That's the second boundary condition. And you can work this out. You end up with equation number 2 and equation number 3. From both equations 2 and 3, you can write b in the term of d, as this the expression, and your a in the term of d. Now let's working on reflection coefficient r for the first case, or electron energy less than v0. Well, in this case, let's consider carefully. K1 is what? Square root 2m e over h bar. So K1 is real. What about K2? K2, you have square root 2m multiplied by v0 minus e, right? So K2 still become real, because your e is equal to 0.5 v0. And since this is your a and this is your b, K1 and K2 both are real, and your reflection coefficient actually equal to b conjugate b over a conjugate and a, and this is your b conjugate, because this is your b. Negative become positive, right? B is to be the same, negative sign. And A conjugate, you switch, this is your A positive, that's turned out to be a negative. And your A needs to be the same, the positive sign. So this gives you R, reflection coefficient, to be 1. What does this mean? So they all reflected back. That's why I have brought down here the reflection coefficient equal to 1. This means that the particle incidence on the potential step with total energy less than the height of the step has probability equal to 1 of being reflected. This occurs with the predictions of classical mechanics, right? Because when you have your E less than your potential, you cannot come across the potential, so they all have to reflect it back. So that's occurring with the classical particles or particle mechanics. Now for V equal greater than 0, that's going to be different. You see that now K2 turned out to be imaginary because your V2 is less than E. So you have for reflection coefficient to be what? 1 minus the magnitude of K2 over K1 square over 1 plus the magnitude of K2 over K1 square. You go back to K2. You go back to B from the previous page. Page number 14. Let's go to page number 13. This is your V, right? Because K become imaginary, so I and I make real. So K2I actual real number. So that's why B conjugate, you don't have B conjugate, you simply become B and B, so that become B squared. You have 1 minus K2 over K1 squared. That's why I have on the page number 14. Right here. You rearrange the term, you end up with R equal to this expression. Now for E equal to 2V0, this is your K1, E equal to 2V0, right? And your K2 to M, that's E minus V0. So you end up with square root 2m V0 over H bar. Trust R equal to 0.03. But for classical particle, for any E greater than V0, there's no reflection, so that's different. This one still have both reflection and transmission. For classical particle, R have to be equal to 0. Okay. For E greater than V0, so it just transmit into the region number 2, no reflection. But this one, some of them still have reflection for the wafer or particle. Now what about C? Ask you to plot the distribution of probability, which is the magnitude of a wave function. That means, of course, in the region number 2, right? Transmitted, which is become the wave function multiplied by the wave function conjugate, where you have the wave function in the region number 2 or transmitted wave that's equal to d exponential negative k2x, where k2 is real because the E less than V0. So this one act like a decay, exponential decay. Actually, I should have this one to be the magnitude of the wave function at square. Okay. Now let's go to the last problem. show that for an electron of energy E, the probability of tunneling through the triangular potential barrier shown below can be expressed as this is the tunneling probability. They want you to verify or derive equation, for probability of tunneling. Hint: use the approximate integral expression for tunneling probability through the barrier of the given shape and neglect the inference on the electron wave function of that part of barrier where E greater than Vx. So let's take a look at the figure. You have what? This is your potential equal to QFX. This is your X. And at the end, you have V0 equal to QFL because this is L. X equal to L. You start from 0 electron, start moving in. And this is your T1, this is T2, that's the tunneling. So the total tunneling that's actually become T1, T2 until Tn. That means you need to integrate. And by using the equation exponential, sorry, negative 2, actually I put this one as the integrate of x1. I will explain to you what is x1 to L. Square root 2m over h bar, square root of Vx minus E. This term seems to be like k, right? In the for V not equal to 0. And Vx is, in the term of x, is the QFX. Well, for x1, we start from the point where the energy of electron equal to the potential energy. So we put our x1 where Vx equal to E. Okay, because we don't care about the lower limit of integration, we just care about the upper limit of integration. So you can work this out from integration. This one is very simple. You simply have x. You rearrange the term, you can end up with this equation T as the given in the problem. T is equal to exponential of negative 4 and 2m or 1.5 over 3qf h bar V0 minus E to the power 3 over 2. So that's how you derive the equation for probability of tunneling. Okay, that's all for the homework set number 2. And this is actually solve problem series 2. Okay, bye.